Okay, sorry about that. So again, I want to tell a story about a generalization of C arrangements and Catalan arrangements. I'm going to talk a little bit about background of hyperplane arrangements, which would be very well known for the sort of expert audience. And somewhere I'm going to wake up people to show something that would be new to them as well. All right. So the title of this slide is Facing Up to Arrangements, which is also Zaslavsky's thesis from 50 years ago, which is a very hard title for the thesis to beat. Now, Zaslavsky sort of studied the phase positive hyperplane arrangements, and he gave one of the coolest theorems in enumeration in sort of discrete combinatorics. So here is a hyperplane arrangement, has 4 hyperplanes. Helen talked about a similar example the other day as well. One of the combinatorial objects that we associate with hyperplane arrangements is the intersection lattice. So, you know, the bottom element is the whole space. The atoms are the 4 hyperplanes. And then we can record their intersections, and they're a little bit different, right? So in the point A, we see 3 hyperplanes intersecting. This one has 3 atoms below it. And the points B and C, each of them have 2 atoms below it. And the red values are the Möbius functions, a generalization of doing inclusion, exclusion on posits. And the way that we build them is that we put -1 on all of the atoms. And then step by step, we assign values on elements above them so that the sum of the elements in an interval is 0, right? So here, if I haven't put any value on A, I have 1, -1, -1, and -1 below it. So I have to put +2 so that the sum of all of those 5 values is 0. Now, when we do that, the statistic that is the Möbius function on the poset has this sort of remarkable application. So on the left-hand side of the poset, I wrote the sums of the actual values of the Möbius function. So it is 4 on this level, it is -4 on this level, it is 1 on this level. And on the right-hand side, I did the absolute values, right? Now, when you add them, something remarkable happens. If you add the actual values, you get a number 1. If you add the other values, you get a number 9. And those have an interpretation of the hyperplane arrangement. This object has 9 regions, and one of them is bounded. So the sum of the absolute values of the Möbius function counts how many regions you have, and the sum of the values of the Möbius function counts how many bounded regions you have, up to a sign. And this is remarkable because, you know, these things just keep track of intersection properties in the poset, and you wouldn't expect that they would have such a reasonable interpretation. Also, this is, you know, a region exists in a real hyperplane arrangement, and the intersection lattice is a much more generic object, right? We don't understand this thing as well as we would like. The sum of the absolute values of the Möbius function is the number of regions, right? So you would like each of the Möbius functions to appear as a statistic on the number of regions. So somehow the proof is recursive, right? And there are interpretations of these as statistics, but they also use that the proof is recursive. Okay, cool theorem. Why is it interesting to combinatorialists since it is about hyperplane arrangements? Well, there are many hyperplane arrangements that are intrinsically combinatorial. For instance, the braid arrangement, as we can easily see, corresponds to permutations. The braid arrangement is the hyperplane xi minus xj is equal to 0. I give you here the one for n is equal to 3. And each region, you can see that all of the coordinates are in some order. So in this region, the first coordinate is always bigger than the second, is always bigger than the third, right? If you orient them properly, that means that you can label that region with, with a permutation 1, 2, 3. So all of the regions of the braid arrangement are naturally labeled by permutations, which is our favorite combinatorial object. What else does it mean in terms of the previous stuff? Well, the number of regions is n factorial, right? So there is a counting formula there. You can generalize it here, and I wanted to draw this picture to remind you that, you know, bigger hyperplane arrangements locally. So this is the hyperplane arrangement for S4, but I've intersected it with a unit sphere. And what I'm looking here really is a line that goes to infinity, and around it I see a smaller S3, which is a Young subgroup in S4. So they have like a localizing structure. Hyperplane arrangements behave well with localization. Okay, now, since the Möbius functions were interesting and I could keep track of them by rank, one could consider the generating function for the Möbius functions, right? So just put them in a polynomial. And as Geren had reminded us, there are 2 ways to do that. This was part of Geren versus Christian's fight. So you can have the generating function for the Möbius function and the generating function for the absolute values of the Möbius function. And the reason that we like the Poincaré polynomial, which is the right-hand side, is that it is actually a Poincaré polynomial. These are the cohomologies of a manifold, which is, you have your ambient space. If it is real, you consider it in the complex numbers, and you subtract the hyperplanes, but, the hyperplanes that are complexified. This is an actual manifold, right? So it will have some Betti numbers, and turns out that these Betti numbers are determined by the absolute values of the Möbius function. Again, all of these things are proved recursively. Now, these objects, because of Zaslavsky's theorem, are polynomials that have nice evaluations at 1 and -1. So here it is the same example as before, and here are the two objects, the characteristic polynomial, which happens to be t minus 2 squared, and the Poincaré polynomial, which is 2t plus 1 squared. This is the same thing, it's just I've reversed the degrees, right? So everything becomes plus, and t squared becomes 1, 4t becomes 4t, and 4 becomes 4t squared. If one factors, the other has to factor. They factor. That's the problem. In algebraic combinatorics, in most combinatorial settings, mathematicians, we suffer from an addiction to things that factor, because if they factor, it suggests that there might be an algorithm that produces them step by step. So we haven't recovered from this. The way that the recursions work is with a deletion restriction that tells you how you can relate the Poincaré characteristic polynomial of an arrangement with one where you subtract the hyperplane and you restrict on a hyperplane. This is very similar to what you do with graphs, the deletion contraction. Graphs. So another type of hyperplane arrangements that you can consider are the graphical ones. You start with a graph and you consider the hyperplanes xi minus xj only for the edges of your graph. And here I give you a few examples. The complete one, I subtracted 2, 4, and I subtracted 2, 4, and 3, 4. And something weird happens. If you calculate their characteristic polynomials, you're going to see that they all factor. Okay, so all characteristic polynomials of arrangements factor. Not only do they factor, I can give you a way to figure out what the positive integer roots are, right? Sorry, the polynomial always factors, but here they factor with positive integer roots. In combinatorics, when we say that things factor, we really mean that they factor with positive integer roots. Maybe with integer roots sometimes. So here there is a filtration of the edges, where you see we keep track of all of the things that end at 2, all of the things that end at 3, all of the things that end at 4. You can do the same thing there, you can do the same thing there. This is similar to the Jussi's-Murphy elements construction. Okay. That's right, I forgot. They sometimes factor. They don't factor all the time. So when you have just a graph that is the 4th cycle, which probably is that arrangement over there if I didn't make a mistake, one of the factors is t squared minus 3t plus 3 that has complex roots that are things that don't exist for combinatorics, so they don't factor. Why don't they factor? They don't factor because the graph doesn't have a perfect elimination ordering, right? Which means a good algorithm to construct the chromatic polynomial of the graph. By the way, the chromatic polynomial of the graph is equal to the characteristic polynomial of an arrangement. That's not very difficult to see. Okay, so hyperplane arrangements are often combinatorial. The characteristic polynomials of hyperplane arrangements have a evaluation that counts how many regions you have, and they often factor. Those three favorite results generalize in particular with the C arrangement. The C arrangement is one of the things that Stanley and I don't know if it happened before it started, but it became popular afterwards, were called deformations of arrangement. So the braid arrangement were just those hyperplanes where xi minus xj is equal to 0. Now I'm going to place a parallel copy where xi minus xj is equal to 1. Right? For each hyperplane, you take a parallel copy and you shift it to the right and you place it. You wouldn't expect that things would behave so well. Like there is no reason that these hyperplanes are going to intersect together and these would. But in the C arrangement case, they do because these are sort of sub-arrangements of the affine Weyl arrangement. It's much more likely that they would have more intersections than expected. Why do we like the C arrangement? Well, it has n plus 1 to the n minus 1 regions and minus 1 to the n minus 1 bounded regions. So here you have 16 regions in total and 4 regions in the middle. And 16 is 4 squared and 4 is 2 squared. This is part of the addiction problem that we're facing. Now, it's not just that they factor that is nice. It's actually their characteristic polynomial that factors as well. This was maybe a little bit different in the creation of the theory. So we'll see later on that these things have versions for Weyl groups as well, and their characteristic polynomials also factor. But somehow we understood that the number of regions factors before we understood why the characteristic polynomial factors. And that was a big deal in how the theory was built. characteristic polynomials factor. It turns out that there is another direction of generalization. We placed all of the copies of the hyperplanes to the right, xi minus xj is equal to 1. I can also place them to the left with xi minus xj is equal to minus 1. Now, this is also a very symmetric arrangement. This is also a sub-arrangement of the affine Weyl arrangement for the symmetric group. And this also has a characteristic polynomial that factors. Now, I write it there as the Catalan deformation because if you count how many regions it has, this is the Catalan number times n factorial. So our favorite numbers together. Don't believe in God, but I mean. And then you can keep going. So you have, you can continue placing copies to the right of, the symmetric interval that you have, minus 1, 0, 1, 2. And then you can go minus 2, minus 1, 0, and 2. And all of those have characteristic polynomials that factor. And for all of those, a number of regions would factor. These are, in other ways, counting parking functions, trees with certain properties. There are many bijections between the regions and combinatorial objects. There is a C arrangement for the hyperoctahedral groups. What would you do? Well, you do the same thing. The hyperoctahedral groups are the coordinate hyperplanes plus not just xi minus xj, but xi plus xj, as if you have sort of like a bidirected complete graph. And then the characteristic polynomial also has this beautiful product formula, positive integer roots here. What do? You place copies not just at where the hyperplanes are equal to 0, but also where the hyperplanes are equal to 1. So, parallel selection of hyperplanes to the right, sort of like there is one direction that is selected here. The characteristic polynomial factors, and it's a nice product, right? T minus 2n to the n. It's a number of region factors as well. Then you can place them to the left and you have the Catalan deformation. And then you can keep going, right? You can add another copy on the right, you can add another copy on the left. And as you keep going like that, you have this sort of weird filtration of the affine Weyl arrangement, and at each point, the characteristic polynomials factor. Why do we care about the C arrangement? It's a little bit unfair. I should say, why do mathematicians care about the C arrangement? That wouldn't be fair very much. But I'm going to show you a bit more about why we care in a minute. But so they started when C was studying Kazan-Lustig cells. So all of these sort of decomposition into gray cells and whatnot correspond to the decomposition of all of the cells, all of the alcoves in the affine Weyl arrangement into Kazan-Lustig cells. And C was studying them, and he realized that it was somewhat there were these regions that the Catalan-Lustig cells would be composed of, and those regions were the regions of the C arrangement. And he was interested in those, so he counted those, but they weren't useful to count the Catalan-Lustig cells, but they sort of like, because they had such beautiful enumerative properties, they created a life of their own. There's something ridiculous that happens. This picture is from Susanna's survey. So all of these things are, the regions of the C arrangement, which are the red regions here. All of them have an alcove that is closest to the origin. This alcove that is closest to the origin is an affine permutation. So it's an element of a group, right? So if you label all of these alcoves for each region of the C arrangement that are closer to the origin with their affine permutation, and you just take the inverse of those elements, somehow, ridiculously, right? There's no reason for that to happen. Somehow, if you take the inverses, they all pack together to a set of alcoves that forms a simplex. How many alcoves are in this simplex? Well, it's a simplex, so it would be, its sizes, the product of how many edges fit in its sizes. So the formula n plus 1 to the n minus 1 in its generalization for Weyl groups is because when you invert the labels of those alcoves, they all fit together in a nice simplex. We also like them because they have generalizations for all Weyl groups. The characteristic polynomial there is t minus h to the n. H is the Coxeter number, but it's also like a hyperplane arrangement, sort of invariant. So h times n over 2 is the number of hyperplanes. So sort of you can understand what this is without knowing Coxeter groups. Okay, but why do we like the C arrangements, right? So this page features the handsome Christian, Stump, and a bunch of less beautiful combinatorial objects. And this is part of the non-nesting versus non-crossing problem or picture or research program or whatnot. So on the right-hand side, I have some of the realizations of the non-crossing family. So I have the actual non-crossing partition lattice here with the labeling or sort of Philippian's embedding into the symmetric group, right, which we know has generalization for finite Coxeter groups. And on the right-hand side, I have a picture of the icosahedron, where the vertices are related by triangulations, and these two are related by sort of reciprocity picture and F2H transformation. And then Christian gave three different interpretations of non-crossing family representatives by using subwords, right? Types of subwords. May they create a subword complex? May they just be subwords? We don't care, right? And on the right-hand side, we have non-nesting partitions here. So notice these are, again, set partitions whose blocks are non-nesting, right? So this block does not appear in the non-crossing ones because it's crossing, but it's non-nesting. And it's weird, maybe you would think that this one nests, but no, you have to have like a whole block to be considered nestable, otherwise. Why do we like C arrangements? C arrangements have a nice way to be labeled by non-nesting objects. So here I actually used the non-nesting partitions, but Christos built all of this picture in terms of anti-chains or order ideals in the root poset, which is another member of the non-nesting family. So I haven't put enough representatives here because we wouldn't be able to see Christian, but and there are too many, right? But the idea is that there are these sort of like two families, each of which has many different realizations of combinatorial objects that work at least in Weyl groups. And inside each family, we have canonical, often equivariant bijections between each of the representatives, canonical equivariant bijections here, but there's no way to relate them. There's no good way to relate them in many ways of defining what good is. Another point that I want to make out here is that you see the way that I drew the non-nesting partitions really models the way that I drew the non-crossing partition lattice. So for instance, there are 4 non-nesting partitions with 2 blocks where the block sizes are 3, 1, and it's the same thing here. And there are 2 non-nesting partitions with 2 blocks where the block sizes are 2, 2. So this is one sort of characteristics that you would call an equivariant relation between them, because the type of the blocks, right, in some sense corresponds to a parabolic type that matches these objects, or to like a conjugacy class of a Young subgroup. So this would be the S3 inside S4, and this would be the S2 cross S2 inside S4. So really, there are many ways to ask to relate the non-crossing and non-nesting partitions. You would like to relate them in a way that keeps track of how these two quantities are identified. You might want to relate them in a way that keeps track of a different cyclic structure that they have. So it's difficult in many ways. So I worked a lot with Mathieu on building and explaining why the enumeration happens in the non-crossing partitions in a uniform way, different than how Nathan and coworkers did it. We weren't able to do the rational ones, but we were able to keep track of all of the equivariant types here, right? So there's sort of like different directions. And these things, as many people have sort of pointed out, are related with rational Cherednik algebras, with the Shuffle theorem, with the representation theory of the coinvariant rings. And to understand the representation theory, you would like somehow to understand the character of the parking space itself, right? Which is n+1 to some power. So this sort of wasn't visible in the C arrangements, and in our attempt to sort of try to create a connection between the two families, I wanted to create structures here that I could find in the non-crossing elements, but that didn't exist yet. So that's the motivation for a generalization I'm going to show you. I forgot. There is this other really cool aspect of the C arrangements. Not only do they, with the regions, match the non-crossing objects, but with statistics on the regions, match other statistics on the non-crossing objects that are topological. So here we have the non-crossing cluster complex. It's dual, really, the icosahedron. And there we had Mathieu's and mine generalization of it in the cluster cluster parking function poset, right, which he talked about on Wednesday. Now, both of these things are simplicial complexes, so they have H vectors. This is sellable. We conjecture that that is sellable, but we had shown that it is Cohen-Macaulay, so it does have positive coefficients in its H vector. This is very easy to see, right? If you just direct the edges in a way, the coefficient here is 1 because this is one sphere. This is less difficult to see, although Mathieu told us that the coefficient here has to be, the dimension of the parking space, so 16. And you can sort of count all of the squares here and imagine them in a torus and maybe convince yourself that there are 16 spheres. Now, these are in fact statistics on the regions of the C arrangement or the Catalan arrangement. So for the C arrangement, the statistic is the number of floors. So, this is the dominant region, and you look at each of the region, how many floors it has that separate it from the origin. It has 1, 1, 1. This has 2 because both hyperplanes are floors. And, this corresponds to 0, this 3 corresponds to 3x, and 2 corresponds to x squared, or backwards, because it's symmetric. In the Catalan deformation, and that was the theorem between, so this goes back to Athanasiadis, essentially. This was between me and Matthew, but we really used Athanasiadis' result. So here, if you keep track of the floors of the regions, but only using the positive sort of translations of the hyperplanes, you still get the statistic that is the H vector of the cluster parking function positive. All of these regions have 1 floor that separates them from the origin. This one has 2, and all of the other regions have 0 floors. But now it's backwards, right? So the 16 regions with 0 floors give you the number 16, the number of spheres. The ones are 13x, and this one. I thought this was really cool. It's also a little bit forgotten because when Christos does a paper, he sort of like completely demolishes the theory, and then there's nothing more that you can do. So then there's no point in reading the paper because there's nothing more that you can do. Okay, family of Shi-like deformations. So I'm gonna start with a tuple of positive integers, and instead of considering the hyperplanes xi minus xj is equal to 0, or then between -1 and 1 and -2 and 2, I'm going to go from minus ni to plus nj, right? So my tuple of numbers is going to determine different endpoints of the interval where I'm placing the parallel hyperplanes, but I'm going to depend on r many parameters, as many as the dimension of my space. We proved with Olivier Bernardi in a combinatorial way that the characteristic polynomial factors and its structure only depends on the sum of the parameters that form this tuple. Here's an example where the tuple is 1, 2, 3, and I have a deformation of the C arrangement in S3, right? So now x1 minus x2 is going to go from -1 plus 1 to plus 2. So I'm going to have a total of 3 copies from x1 minus x2. For x2 minus x3, I'm going to have a total of 2 plus 3 is equal to 5 copies. And for the other one, I'm going to have a total of 4 copies. Right? They're placed in a way that is explicit, but not visible in the picture. So this one, our theorem says, has characteristic polynomial t times t minus 6 squared. But then I can do the same thing, but with another vector of numbers, 1, 4, 1. And it's obviously a different hyperplane arrangement, but our theorem says that it has the same characteristic polynomial, right? So in particular, it has the same number of bounded regions and the same number of total regions, which is weird because they look very different. And the number of regions that they would have is, n plus 1, but not to the whole dimension of the space, not n plus 1 to the n minus 1, but n plus 1 to a smaller number that corresponds to the number of cycles of your permutation. So the regions here are counting fixed points in the action of the parking space. You mean starting with 2 copies of parameters? That one didn't work, so it didn't have a factoring structure in the characteristic polynomial. Not everything works. No, it's a good, yes. No, it's not, and it's a little bit weird. They're not symmetric, right? Because they depend on the parameter there. But I'm going to tell you afterwards how they're defined in a sort of way that fits more with Weyl groups, because I would like to understand them better in this way as well. Yes. Yes. I mean, every I don't know. Yeah. So this is I want to talk more about this when I explain a little bit how they're constructed, if there is more. Okay, so then there is also a version of the Catalan deformation, which is like the same idea. Instead of starting from, so before we were at minus ni plus 1 all the way to nj, now we are between minus ni to plus nj, right? So it really models how the Catalan deformation is related to the C deformation. And it's the same picture, and I'm impressing you here with 2 arrangements that again correspond to different vectors, and they look very different, but they have the same characteristic polynomial. So now I'm going to tell you a really cool way about how to construct them in general types. And I'm going to remind you a few things about these ideal C arrangements that maybe are not as well known as they should be, because I think part of the reason is that they initiated with the Japanese groups and there wasn't enough overlap with the rest of the Combinatorics community. Okay, so briefly, a reflection group is a finite subgroup generated by reflections. I don't care so much about anything here. I was putting a few slides for students in the audience, but I just wanted to show a few pictures. So I'm going to focus on the Weyl group, which is the crystallographic condition mean that this coefficient that determines the reflection is an integer. And the things that we have in Weyl groups is the reflection arrangement here. Instead of the reflection arrangement, we can consider the root system, so the roots that define the reflection arrangement. But then we can keep track of the standard order between the roots, which means how can you write the non-simple roots as integer combinations of the simple roots. So here I start with sigma 1 and sigma 2, and sigma 1 plus sigma 2 is on top of it, and 2 sigma 1 plus sigma 2 is on top of that one. Now this is the root poset in the Weyl group. This is one of the best representatives for non-nesting partitions, because anti-chains here, or equivalently order ideals here, correspond to non-nesting objects. All right. Now, I'm going to show you a way to construct a family of hyperplane arrangements, sort of using these ideals. So in the previous pictures, we saw how to go from the braid arrangement to the C, and then to the Catalan, and then to the next C, and then to the next Catalan, and then to the next C, right? And this thing would create a filtration of the affine reflection arrangement for the symmetric group. But it's a filtration that's not perfect, because at every point you're adding a bunch of hyperplanes. There is a way to create a filtration where at every step you're adding one hyperplane. Okay? So you start with an order, you start with an ideal, and you are recording the hyperplane that corresponds to this root. Then you continue so that the other root that you select, it keeps forming an ideal, and you add the other hyperplane. Then you continue, and I'm still forming an ideal, and I've added the third hyperplane. Then I continue, and I'm forming an ideal, and I added the fourth hyperplane. These are the ideal subarrangements of the braid arrangement, and they all have characteristic polynomials that factor. In fact, are free, and it's very easy to predict the integer roots of this polynomial. So you're sort of keeping track of the heights of the roots that you have, and you're taking the dual partition of that. Now, when you completed this structure, you remove one root, so that the remaining ones are still an order ideal. But the root that you remove, you're placing the parallel copy on it in your hyperplane arrangement. I remove another root, and I'm placing the parallel copy of it in the hyperplane arrangement. And then these polynomials still factor. And the integers here, again, are predictable. I sort of start with the roots in the braid arrangement or in the original reflection arrangement, and I add something that has to do with the heights of the roots that I selected. So I remove another one, I add another root. When I've removed all of them, it means I've added a parallel copy in all of them, and now I have reached the C arrangement. Then I can start going backwards. I start creating an ideal, and I add a root on the other side of before. I start creating an ideal, I add a root. I go on like this, and at every point, I'm having a hyperplane arrangement that is free, whose characteristic polynomial factors, and the factors are predictable. I think this is a really cool theorem. Again, abstractly, it says there is a free filtration of the affine Weyl arrangement, meaning at every step of the process, the subarrangement that you have is free and the exponents are predictable. Okay, why is this interesting? See what happens in this example where I have a deformation of the type B situation. The red hyperplane is my active hyperplane, the hyperplane that I have just added at the very last stop, at the very last point of it. When I'm removing this thing, it means I'm adding the last hyperplane to get the C arrangement. Now, the hyperplane, the characteristic polynomial before I add the red thing is t minus 3 times t minus 4. The characteristic polynomial when I add the red object is t minus 4 times t minus 4. Because my root poset only changed in one position, I know that only one of the factors will change. But then the deletion restriction property tells me that I'm forced to have that the restriction of the hyperplane is going to be the factor that didn't change. And here I would have like a bunch of them, right? So a product of many factors, only one changes. So the characteristic polynomial of the restriction is the other stuff. So you can do the process in a way that is controllable so that you restrict sequentially on well-selected hyperplanes, and what you get is always a product of t minus the Coxeter number to some power that corresponds to the dimension that you're at. So my theorem, I'm going to tell you a little bit more about it. This says that for every flat z of my hyperplane arrangement, I can construct a deformation of the restriction az such that its characteristic polynomial is t minus h to the dimension of the flat. So again, the number of regions here would correspond to fixed elements in the action on the parking space. I don't know how to label them with this way. I would love to be able to do it, but this is what I wanted to construct. The existence of these things is remarkable, in my mind at least, and partially because the restrictions of the Weyl arrangement are not Weyl arrangements. They don't have a good reason to sort of have deformations that behave so well. And look at the other things. The restriction on this red line is one of my examples. So just looking at the red line, the restriction of the hyperplane arrangement is just a single point, and the deformation is adding the other 3 blue points. And the deformation has characteristic polynomial t minus 4, right? Because it has 4 points. But look at it, they're not equally spaced. In the Shi arrangement, in the Catalan arrangement, everything is equally spaced. These ones are not. So for the experts, I wanted to wake you up now and to show you a definition that you haven't seen that sort of naturally generalizes the definition of the Shi arrangements for Weyl groups. So Christian a while ago explained to me that the best way to think of a natural coordinate system for a restriction, for a flat of your arrangement, is to take the co-weights that don't live in the roots of that flat. So there is sort of like a natural duality there. So for every subset of the simples, the co-weights that correspond to the complement of those simples form a natural coordinate system for the flat that is the intersection of the hyperplanes for the simples. Okay? In particular, if your set J is the full set, if your set J is the empty set, then you have the whole space and you have all of the co-weights as natural coordinates. Every root can be restricted, so literally project in a particular way, but I'm using the word restrict here because it depends on the inner product, but you can restrict on the flat xj by sort of getting rid of the coefficients for the simples that are outside of your, that are inside the set that you selected. Because these are, the co-weights are the coordinates that you want, and the co-weights are orthogonal to the simple roots. Okay? If you do it like that, this is a way to write down the restriction of the hyperplane arrangement. So instead of a root of your ambient root system, you're taking its projection on the flat, and you're forcing the inner product with the omegas that are outside your set J to be equal to 0. Now, different roots here might have the same projection, right? So it's not that you're going to have that many different hyperplanes, but this is a good way to express all of them. So this is a root theoretic way to describe the restriction of the reflection arrangement on a flat X. If I have this way, here is how I describe the C deformation of the restriction. My roots are the R sub J's, my roots in the restricted flat now, in the flat Xj. To be able to write an equation, I have to say, I have to give a formula with the coordinates of my flat, which are the omega J's when J is outside of my subset. Okay? So what is the formula? The inner product of these things should be epsilon, where epsilon is 0 and 1. Now, if I stop here, that's the definition for the C arrangement. Right? So the C arrangement stops here. And I'm saying now, apart from epsilon, you have to subtract the inner product of the original root with the sum of the co-weights that are in your set. It's very explicit, is my point. It's not root theoretic. It's not exactly clear why it would work out, although it's compatible with the previous definition that I gave. But it's an explicit formula, and this structure will always give you this factoring characteristic polynomial. Let me show you an example that I semi-prepared here. So this was again the definition, right? This is how this would be like a linear form in the coordinates inside my flat, and this would be what is this linear form equal to. So this would be a number that is 0, 1, 1, 2, something like that. So let's say that I want to focus on E2, 3. So here my flat is the intersection of these two hyperplanes. And so its coordinates are the co-weights for this root and for this root. So omega 2 and omega 4. So this is omega 4 direction, this is omega 2 direction. So I want to see what happens for the roots that restrict to omega 2. Now, all of these roots, when they're written in terms of simple roots, they only use the two red ones or omega 2. So when I restrict on my flat, the two red ones are going to cancel out, they're going to become 0. So all of these four roots, the restriction on my flat is the root of E to 3. Okay? So to see sort of, and this, the inner product here would be, you know, omega 2, omega 2, omega 4. So it would just give you some equation for omega 2 is equal to something. So this would correspond to the vertical lines here. Omega 2 is equal to what now? Epsilon is 0, 1. And here are the inner products that I take with these four roots. So this one is going to give me inner product 2 when I pair it with omega 1 plus omega 3. This one is going to give me inner product 1. This one is going to give me inner product 1. And this is going to give me inner product 0. Okay? So this quality is 0, 1, 1, and 2. And this quality is 0 and 1. And when you subtract them, the things that you can get are 1, 0, minus 1, minus 2. I don't want you to follow me here on the particular definitions, right? I'm just saying it is really something that is predictable. It's not a difficult thing to calculate. And these figures look surprisingly similar to the figures that I drew before for you. They're not because I drew omega 2 and omega 4 to be orthogonal, but that's just like an affine change of coordinates. So this is how the pictures look for all of the rank 2 restrictions of E6. I thought these were very surprising. So here I'm selecting the simple roots that I'm intersecting their hyperplanes to sort of get a flat of rank 2. And all of these sort of colored lines are the deformations that I have defined with my previous formula from the roots of the arrangement. Again, many roots might give you the same deformation, but it doesn't matter. There are some behaviors that are interesting. So it's very clear to see that this is indeed a deformation of the restriction. The restriction of E6 on this flat of type D4 will have 3 hyperplanes. This one will going to have 4 hyperplanes, right? One thing that is interesting is that it's visible here that the restrictions are not always Weyl arrangement. For instance, here, this hyperplane arrangement has 5 directions, right? So the original restriction of E6 on this flat is going to have just 5 lines, and there's no Weyl arrangement with 5 reflections. And I'm claiming, surprisingly, that this deformation gives you a characteristic polynomial that factors, and it's always the same. It is t minus 12 squared, because 12 is the Coxeter number for E6. I don't know if you can see it all the way in the back, but these are not equally spaced. Some of them are. This is equally spaced, but here you have a bunch of hyperplanes that are 1 apart, and then you skip a little bit and it's 2, and then you skip a little bit and it's 2. It's impossible to do it if you don't have that, right? Like you can show that it doesn't work in cases. Okay, so we have, you know, a surprising way to extend the picture for C arrangements to all of the restrictions. And here come all of the possible questions, right? There are all of these different ways to label regions of the C arrangement. What else could you do here? Guess we're close to the answer. You can ask me questions about it at the end. I wanted to show you one last thing that has to do with the labeling. So I don't know how to do the general Weyl group picture yet, but I think it's a very interesting research program. But we do know how to do the type A case because I'm working with Olivier in Brandeis, and Olivier has created this remarkable, very general story where if you have arbitrary, almost arbitrary deformations of the braid arrangement, you can label the regions by certain types of trees, and then if you're trained in French mathematics, you can count those trees, right? So in our case, for the C deformations, the way that I defined them before looked much simpler because it had this sort of like symmetry for left and right, but it is equivalent to the root theoretic definition. And the way that we counted the regions here is by showing that they're indexed by the sort of MRE trees that have certain conditions for their labelings. This one is just a C arrangement, so the condition is that the labeling is decreasing on the right and can do whatever it wants otherwise. And so the way that you count these trees for the C arrangement is easy. In the general case here, I didn't really know how to do it, but at some point I was explaining to Guillaume how the filtration works, and I was like, well, you have this big system where you can go all possible ways, and it always works. And then, sorry, I said Guillaume to Olivier, and then Olivier came up with this remarkable generalization of the Weyl bijection. So the Weyl bijection is one of the cool ways to count trees by bijecting them to functions. And we did the sort of a similar thing here. All of the trees that appear here have their own different bijection to a class of functions, and those are much easier to be enumerated, and it turns out that they're counted by the sum of the ni's plus 1 to some power. So we had like a very satisfying answer in labeling them in type A. Okay, that's it for now. Thank you very much.